Let's start with 43, isPower. Okay, so we want to determine if the given number is a power of some non-negative integer. All right, so non-negative integer, what do we mean by that? Basically a whole number, one that's, not negative. So something like 0, 1, 2, 3, whole numbers, okay. And then, in fact, it has to be at least one. So they could have just said a positive integer, right? Non-negative would imply that it could be 0. Anyway, subtle but important difference. So we're looking at this and we want to know, could it be a power? So first of all, what do we mean like could it be a power? Well, it could be like a square, it could be a cube, something like that. When I was running my math tutoring business in a former life, what I used to tell my students is that you should know the following powers. Okay, so you should know all your squares up to, I think 15 is what I said. So like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And we'll go on with these, but basically the idea is that you want to know, you want to be able to recognize powers. When you're doing math, you want to be able to just see them and know them, basically. That's the idea. I'm kind of distracting myself here. But okay, so 100, 121, 144. I'm running out of room, but 169, etc., all the way to 225. I also recommended that my students know most of their cubes, or at least some of their cubes. So let's see how many I know. It's probably not that many. So 1 cubed, 2 cubed is 8, 3 cubed, 27, 4 cubed, 64, 125, 256. And this is where it gets a little fuzzy, but I think this one's 343. And then I'm not really sure. 512 if I had to take a wild guess, and then 729. And of course 1,000. So, okay, we should be able to recognize these as well. And this is like, when you're in grade 12, you're doing logarithms and stuff like that, or at least that's grade 12 in Ontario, but like pre-calc kind of stuff, right? After that, for other powers, I basically recommended that they know all their powers of 2, up to probably about 2 to the power 12. The main one I recommended that they know is 2 to the power 5, because it's a good sort of pinning point. If you can remember 2 to the power 5, it's not too hard to jump off from there, because if someone asks for 2 to the power 4, well, it's just 2 to the power 5 divided by 2, so it's going to be 16. If someone asks for 2 to the power of 7, let's say, we're just going to multiply this one by 2 twice, so it's going to be 128. Or also known as multiplying by 4. Anyway, the point is, we want to know our powers because you need to be able to quickly recognize these things. It really speeds up the process of evaluating logarithms. But we're not here to evaluate logarithms. We're here to identify powers. And that's kind of an interesting thing because if you think about it, this is a really open-ended question. Basically, well, actually, I'm kind of realizing something now. Pretty much, like, I wrote down a lot of the powers that actually fit within this range here. So we could probably just have an array of them and be done with that. In fact, let's start with that. Might as well, right? So we'll say, should we use a set? Yeah. Const powers is new set. It's got nothing in it to begin with. And we're going to say for let base be assigned the value of, how do we want to do this? Base is going to start at 1? No, it shouldn't be 1. It should be 2. Yeah, it should be 2. And can we do this? Can we just put a single element in there, or does it need to be an array? I'm thinking it needs to be an array, but let's just make sure of that. So, oh, yeah, well, let's just clear that for now. Undefined is not a function. What? Okay, hold on a sec. Console log powers, new set, 1. Let's see if it works like that. Okay, yeah, good. So we need that. Okay, cool. So yeah, just to get that stuff back, and then I'll put that in there. Cool. So we've got this thing. It starts with 1. Why am I starting with 1? Well, because basically I want to do a nested loop here, which maybe this is the intended way to solve the problem because we are in the, what is it, labyrinth of nested loops. Yeah, cool. And then at the end, well, and Rainbow, the reason I didn't want to do a return on that set there is because if you do a return, it actually, it doesn't really work. You can't really see what's inside, at least not in this environment here. So for a console will tell you what's in there. And, oh, hold on a minute. We've got a donation from our guy ATD285. $10 saying, when you were talking about deciding if you're going to continue doing these streams and previous tasks, it made me realize how thankful I am for you sacrificing your time for these. Wow, ATD, I gotta say, I mean, getting a message like that, that's why I'm in it, my man. So, hey, thanks a lot. I appreciate you taking your time to watch these and contributing in the chat and all that. It helps. So, okay, you guys are the best. Let's continue with this. So we've got this. We've got base, and we want our base. Well, eventually we're going to do something like this, okay? Plus plus on that. And there'll be some condition. We'll fill that in a minute. But, anatomy here. We got to talk about this. So we've got a to the power of b. So, okay. When we're looking at this, and this is like kind of counterintuitive, a lot of people tend to get this mixed up, but basically when we're talking about this for a power, this part is called the base. And I probably should have used a b for that, but oh well. And I probably should have used an x for this one because this is the exponent. Okay. A lot of students get confused between exponents and powers. This is not the power, this is the exponent, okay? The power is this whole thing. So that's really, really important, okay? When we're talking about a power, we're actually talking about the result of doing something to the power of something else. So a base to the power of an exponent, that gives us a power. So the power is the actual result from this. Okay, cool. Good with that? Great, let's move on. So we've got this. What I want to do is basically, I'm going to increment the base. So the base is going to start at 2. Why not 1? Well, I'll show you because I'm also going to increment the exponent. So the exponent is going to start at, now hold on a minute. I'm just realizing something. Yeah, okay. I'm glad they specified this where b is greater than or equal to 2 because otherwise like everything's a power to the power 1, right? Okay, cool. So let exponent be 2. We're going to have another condition in there and then exponent plus plus. Now, what specifically are we checking here? Well, we want to do something like this. So we want to say, okay, here. Let's do something like this. Const power is assign the value of base to the power of exponent. Okay, basically something like that. Power is base to the power of exponent. Cool. And then what are we doing with that? Well, basically just put it in here, right? But maybe we should only do that if it's less than or equal to 400. So we'll say if power is greater than 400, break. Get out of there, man. And otherwise, if it's not, well, just put in the set. What is it? Add? Is that how we do it with the set? I think it's add, but let's try it. Powers.add. Thing is, this loop out here is going on forever. This one here, yeah, it looks like it is, but it's not because of the break over here. So we should probably give a condition here. What we want to be sure of is that if we were to take our base and multiply it by itself, it would be less than or equal to 400. Because otherwise, we already know, like, the lowest exponent is going to be 2. If we know that when we square it, it's going to be something above 400 anyway, then yeah, no sense in continuing. So we'll do that. And then at the end, I'm going to do a console log of powers. And then I'm also going to do a return, if I can spell the word properly, of powers. Oh, Rainbow's got to go. Okay, well, thanks for watching, man. You want me to look at yours now or afterwards? I don't want to like spoil the problem. You want to tune into the VOD? Because I will go over it. Either way, thanks for tuning in, my man. And I'll see you later. Okay, so we got this, and this is the reason why I was console logging before, because otherwise we can't tell what's in the set, right? For whatever reason, when we do a return, it doesn't actually give us the contents of it. So we've got a bunch of powers in here, And yeah, it looks like they're all good. They're all below 400. There's not really that many of them that I'm seeing. So we're starting with our powers of 2 and then our powers of 3. Yeah, okay. Wait a minute. Did it skip 4? Oh, yeah, yeah, it kind of did because all the powers of 4 are also powers of 2. Cool, cool, cool. Yeah, that's neat. I like this. Okay, so that's the beauty of a set. It's not going to repeat elements, right? Like the mathematical definition of a set is something where repetition is ignored. Repetition doesn't matter. So like a set containing 2, 2, and 5 is the same as a set containing 2 and 5. No difference. And also the same as a set containing like 1,000 2s and 500 5s. Okay, so for this, we've got our set here of all of our powers. Could we just do something like this? Return powers.has n? Yeah, we could. Turns out it can be that simple. So good stuff. All right, now just a couple things to talk about here because I didn't actually fully address the fact or the reason why I put this in here. The reason is because if I had started base at 1, then every power with a base of 1 is just going to be 1. So this would actually just keep going forever. It would never break because it would just be 1, 1, 1, 1. It would be like, well, is it above 400 yet? No? Okay, well, keep going. So important that we started off with a 1 because 1 is a power after all. It's 1 to the power of anything, right? So, because they say B has to be greater than or equal to 2 here, but they don't say that A does, right? A could still be 1. So, good to have that in there. Cool. So, that's using a set. Lots of nice things about set. So, the first thing is that repetition, like we said, is ignored. So, that's nice. It keeps it nice and lean. We don't need to say, like when we're doing add, we don't need to say, well, if not powers dot includes this element, then like push it in here or something like that. The other thing is it doesn't actually, well, hold on a minute. My understanding was that it doesn't have an order in the sense that like we wouldn't be able to do something like powers at 2, right? But I kind of get the sense that it is an iterable because we can do something like this, right? Like we can return an array of all the powers in there. And then I guess it's just, yeah, in the order that they were found sort of thing. I'm wondering if we could run a loop on it. That's, yeah. Could we do that? For const p of powers, let's say, and we'll just do like a little console log of p. Yeah, let's try that. Yeah, okay. So we can iterate through a set. So I guess there is some kind of ordering on it. But the other nice thing about it is, like I said, we don't have to check for repetitions before adding something. And also, look, the syntax is nice too. Like even for something like code golfing, this will save you characters. Better than like a push or an unshift or something like that. We don't have to do an includes. Has is, yeah, a lot shorter than an includes or an index of or something like that. So yeah, a set, it's a good thing. It's a good thing. Yeah, it's nice. Okay, so this is one way of solving the problem. Now, a lot of other people look at this problem in kind of the reverse way. They start with the number itself and they say, well, could we take the square root? Could we take the cubed root? Could, you know, et cetera, and basically see if we get something eventually that's like a whole number. So, whoops. Wrong kind of select all there. All right, so let's do this. Let's put, whoops. Yeah, there we go. Good stuff. Basically, we want to do something like this. So for let b be assigned the value of 0, not 0, let's make it 2. And while b is less than 10, let's say, I don't think we're going to be able to take the 10th root of anything. Because 2 to the power of 10, well, that would be the same as 2 to the power of 5 times 2 to the power of 5, right? So that's 32 times 32. So that's 1,000. Wait. Is it 1,024? I could be wrong about that. But either way, it's above 100. So, like, no power of 10 is going to fit below 400. unless it's 1 to the power of 10, in which case we would already have found it. So we'll run through this loop, and if we don't find anything, we're going to return false at the end. If we do find something in the loop, we're going to return true right on the spot. We're not even going to wait till the end of the loop. We're just going to, boom, return it. Kind of like this one is just breaking right after it realizes none of these powers are going to be small enough after this. So, okay, we've got this, and what we want to say is, like, you know, we've got this, like math.square root, right? That's something we can do. But I don't think we really have a math.cube root, but we kind of do in a sense. So this is an exponent law we should all probably be familiar with. If you're not, don't worry about it, but it's one that gets taught in school, usually in Ontario, grade 11 university courses, grade 11 university bound math courses is what I mean. They sort of teach you this. So if you have, let's say, b, and you want to take like the nth root here, okay? Oh, there's a name for that. I think it's called the index. Anyway, this is the same as b to the power of 1 over n. Okay, so we don't need like a cubed root or a fourth root or anything like that. We can just raise it to the power of 1 over 3 or 1 over 4, and it should sort of give us what we're looking for. So I'm just going to do a little console log on this for now, and we're just going to do math.pow of n and 1 divided by b. Okay, where b is the, wow, I sort of flipped those in the last one, whoops. Okay, check it out. So notice we've got a bit of an issue with this, which is that this should be 5, like this should be exactly 5. And it's not quite, so not exactly a whole number. So what do we want to do here? We want to check, is this thing going to be close enough to a whole number, right? Maybe, okay, let me just check if I would get any different kind of results if I did it this way. I'm suspecting I won't, but we'll see what happens. Yeah, it looks about the same. So, okay, these are all false. None of these are really that close to a whole number, like 2.04, I guess, but we're looking for more like the kind of thing that's, well, okay, that one was right on. But we're looking for the kind of thing that's going to be like really close to a whole number. Like, well, okay, this one is whole numbers in a bunch of spots. Well, hold on a minute. If this was a whole number, then what would that even look like? It would mean this basically, right? Like mod 1? Yeah, mod 1? If we did mod 1, then it would be 0, right? That's what it means to be a whole number, I think. So I should probably wrap this in a conditional and basically say something like if this is the case. So if this, then return true, you know, something like that. And I think this is going to pass some of them, but not others. So the ones where it was exactly right on, it'll pass. For the ones that aren't, like this one, or for the one that wasn't, I guess, it's not passing. So what do we want to do with this? Well, we basically want to say, is it close enough? Well, what does that mean? You know, what do we mean by close enough? So let's say const, actually, because we're not going to reassign this within the loop. So we'll say const root is going to be this thing right here. So root is this. Whatever root it is, you know, second root, or I guess we call that the square root, the cubed root, etc. And then here we'll say that. So I think so far I've just rearranged. Yeah, still 9 out of 10. So what do we want to do with root? Well, basically what we want to say is, well, is it close enough to 0? So the problem with this is right now it could be like 0.999999999999999. So that's really close to 1, actually. So what I'm going to do is I'm going to just add a little bit. I'm going to add a very small number onto root just to sort of tip it over so that it ends up necessarily being a bit above the number instead of above or below the number. So this is going to put it a bit above. And then we don't want to say that it's equal to 0. We want to say that it's less than or equal to 0.0001. I don't know. I'm choosing those kind of arbitrarily, and I do think this is pretty messy, but yeah, it looks like it's passing the sample test. I guess it passes the hiddens as well. And the fact that we're seeing this here now tells us, I guess we didn't check downstairs. This is kind of funny. You solved isPower? I don't believe it. You did that? Wow. Amazing. Okay, cool. So great. We'll close that for now. I don't like this. Okay, just being clear about that. I do not like this. I think it's very bad. So why? Well, because it's sloppy. Oh, geez, doing that again. Okay, my mistake. It's sloppy. It's sloppy as heck. Like, if we look at this, you know, I don't want this kind of junk in my algorithm. I don't want, like, is it close enough? You know, what if by fluke it was just like really, 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 really close? You know, like what if? Okay, let's just imagine that the constraints were different and that we were able to go up to much bigger numbers. So we could say like. You know, we've got 10 to the power of 10, for example, and that's like 10 billion, right? So if we were to do 10 billion and 1 and then take the 10th root of that, it might actually be close enough that it would pass this despite not actually being a power. Does that make sense? So that's basically my issue with it. Okay, so moving on with this. Well, I guess with all the trash I'm talking towards this algorithm over here, I should probably come up with something a bit better. I guess we had this one down here, which was pretty not bad, but it's got this nested loop thing, and I'm thinking if there's another way, you know, like maybe a smarter way, because this way, okay, let me back up a second. There is something I really like about this one over this one down here, and it's the fact that this is basically just like shots in the dark, you know? It's like, okay, well, what if the base is 2 and the powers are the exponent's 5? What if the base is 7 and the exponent's 2? You know, it's just like trying them out randomly. It's just like fumbling along. And also this would crumble if our guaranteed constraints were less forgiving. If we had like huge numbers here, well, this would take forever. We've got nested loops, man. Come on. Anyway, the point is, moving on to this other method we're about to do, I really like this strategy. I think it's going to be a good one. So what we're going to do here is let's talk about powers. Yeah, let's talk about powers. Let's talk about what powers are all about. So first of all, let's get some nice colors in here that we want to work with today. That's a nice one. Okay, we'll go with that. And then let's get another one in here. Yeah, why not? And actually that one's kind of bright. Maybe we'll get like a bit of a darker one. Oh, wrong way, towards that edge. Yeah, okay, that's cool. And yeah, why not? Okay, so we got some cool colors here. And I'm going to start by using black. Anyway, okay, we'll increase the pen size. Now, what are we going to do here? We're going to talk about powers in terms of their prime factors. So, anyone have a power they want to take a look at? Any suggestions here for what power we should use? We'll take a look at a few examples, but why don't we start with something like, let's go with 125, whoops. Oh boy, it's been a long day apparently. 125 and then 36. Let's go with those examples for now. So if we think about the prime factors for 125, well, there's actually kind of a cool way of doing that. I don't know if you guys have seen this before, but it's called a factor tree, and it's a really, really useful tool. So check this out. Just think of two numbers that multiply to 125. So what are two numbers that multiply to 125? Well, it could be 5 and 25, right? If you have 5 quarters in your pocket, you've got $1.25. So 5 and 25. Well, 5 is prime. We can't go any further than 5. It's already a prime number, so we'll stop there. But 25, well, we can go further. So this is going to be 5 and 5. And now something we notice is that, first of all, we have only prime numbers on the leaves, okay, as we always will. And furthermore, it's not just any prime numbers, it's the exact prime factors that are going to multiply to give us 125. So 125 is going to be 5 times 5 times 5. That's basically the idea here. Okay, so then, all right, that's pretty good, right? If we're able to find the prime factors, then that might help us, because we can see the prime factors are all 5s here. So if all the prime factors are the same, well, then it must be a power, right? That makes sense. Okay, cool, that makes sense. So I guess it's probably that simple. Let's just verify it for 36. So I don't know what we want to say here. Maybe like 3 and 12 for this, for 36. There are other ones. We could have done 9 and 4, but it's up to you. Anyway, we've got 3 and 12. 12, we can go further. So maybe we'll say it's 4 and 3. And 4, we can go further as well. We can say it's 2 and 2. Okay, well now this is a bit different because what we found before is that our prime factors were all the same. Now we're finding that that's not quite the case. We find that actually it could be a situation where they're not all the same. So it could be something like this where, for example, 36, wrong tool, there we go. So 36 is not, well, yeah, okay, we could say it's like 6 times 6, but 6 is 2 times 3. So we get 2 times 2 times 3 times 3. So that's still a power, even though the prime factors aren't all the same. But what is true about them is that we have the same number of each of our prime factors. So we've got 2 2s, 2 3s. Now, if it was 2 2s and 3 3s, that would not be a power. That would, I think, be 108, and it would not work for us. So what we need to make sure of is that in our prime factors, however many of them there are, maybe there's only one like type, one unique number in terms of our prime factors, one unique factor, okay? So if that's the case, if there's just one unique factor, then yeah, of course it's a power. If there's more than one unique factor, then we just need to make sure that however many of them there are, it's the same number for all of them. And if that's the case, then yeah, we're talking about a power as well, okay? So basically this one is a special case of this in the sense that, like, what I'm saying is look at all your different prime factors, look at how many of them you have, and if that number of how many you have is all the same, then we're done. It's a power. But then you might say, okay, well, but if there's only one type of prime factor, then how can we even make that comparison? Well, good, you're done. Of course they're all the same. If there's just one of them, how can they not be? Okay, so that's going to be the plan. All right, we're going to talk about this in terms of prime factors. So let's start with that. Let's get our prime factors in here. This will be fun. I don't think we've done this yet. Correct me if I'm wrong. We might have, but if we have, it's probably been a while. So prime factors. Prime factors? Whoops. Okay, my mistake. Anyway, okay, so prime factors of what? Some number. Okay, we'll call it num. All right, how are we going to get the prime factors? Well, first of all, let's let factors be, we'll start with just an array. Yeah. And we're going to return the factors in the end. And I'm going to return outside here prime factors of n, the number that we're starting with. Actually, wait, let me start with something that we know. So let's try 125 and then we'll do 36 maybe. Okay, so our prime factors, well, what are we going to have in here? We're going to say 4. Let d for divisor, be assigned the value of 2. Why are we starting at 2? Because if we start anywhere less than that, if we were to start at 1, then, well, we could divide anything by 1. We know it's a whole number, so there's no sense in checking for 1. We know everything is going to have 1 as a factor. 0? Oh, don't even get me started. You want to try dividing by 0? I don't recommend it. Anyway, okay, so we'll start at 2. And we want to continue this while the number is greater than 1. That part might seem a little strange, it might seem out of place. We're initializing this variable d, and then we're talking about how we're going to modify that, but we're not checking in terms of d here, we're checking in terms of num. So specifically, why are we doing that? Well, basically because we want to divide this out as much as we can. So we'll say while num mod d is 0. So in other words, while we can divide by d, let's do that. So we'll say factors.push d and num divided by equals d. Let's actually divide it out and we'll push it into our factors array here. Okay, so I think that's all we need in there actually. So let's see if that works. We're expecting an array containing 3 5s. Nice. Let's try 36. We're expecting an array containing 2 2s, 2 3s. Good. Let's try 108. We should expect 2 2s, 3 3s. Which makes it a very remarkable number. There we go. Okay, good stuff. So we're getting all of our prime factors here. That's nice. And that wasn't too bad. And let me know if anyone has any questions on this. I should also mention, I believe there's probably a better method than this, you know, because you might be looking at this and thinking, well, why are we just doing d++ every time? You know, like, doesn't that mean we're not just checking the prime factors? We're checking any kind of factors. And yeah, that would be true, but because of the while here, actually turns out not to be the case. Because you might think like, okay, so it's going to start at 2, then it's going to go to 3, then it's going to go to 4, right? So, but you don't want to check for 4 because that's not prime. The thing is, nothing would be divisible by 4 by the time it gets here because we've already divided out all the 2's from the number, okay? Because we are modifying num here. So if we've divided out all the 2's, where are you going to get a 4? Okay, makes sense. All right, great. So basically we've got this now. This is telling us, yeah, this stuff. I actually want to change it up a bit though, because what we're interested in here is not so much like the exact prime factors. We want to know what type are they and how many of them are there. So let's say let instances start at 0. This is like how many times it divides in, right? Maybe I should call it divisions. Instances is probably fine. And basically we'll say if instances, if you did find some of them, oh boy. Okay, if instances, if there was at least one of them, okay, so as long as this is not 0, then what we want to do is we want to say factors at d is assign the value of instances. So now when we run this, factors.push is not a function. That makes sense, right? So instead of that, we just want to say instances plus plus. And it looks like I'm having a really hard time with this word, and yeah, I am. Anyway, let's see what happens here. Great, so 2 2's, 3 3's, that's 108. If we were to do 125, we should expect to have a key of 5, value 3, perfect, what we're looking for. Great, so what do we want to do now? Well, basically, we have something that's going to give us our prime factors. It's going to tell us specifically how many of each we have. What we want to do is basically go through and see, are they all the same? Is there the same number of each one of them? And we found that that should work, right? But, now you got me thinking. Let's do another example over here. So I specifically want to look at 144. It's a great number. If you're not familiar, oh, get to know this one. It's great. Anyway, so let's see. 144. Well, as I recall, this is 12 times 12. So let's start with that. Make it nice and even, nice and easy. And that also tells us right off the bat, yeah, it's a power. So we should expect to return true for this one. 12 is 3 and 4. This 12 is also 3 and 4. We've got some real symmetry going on here, which I'm about to break by doing it this way. But anyway, that's fine. So there we go. If we look at the leaves on this factor tree, we've got 3, we've got 2, we've got 2, we've got 3, we got 2, and we got 2, which is telling us that this number, 144, it's not actually exhibiting the property we might have expected. So 144 is going to be 4 2's. I'll write it this way, 4 2's and 2 3's. Okay, so basically these numbers over here, they're not the same. They're not the same. So what needs to be true about these? Well, basically, we just need to be able to divide out something from these numbers. That's it. You know, if you think about it, that's it. Because if you take any number, you know, any number is going to be like some group of factors, right? Like I usually like to think about numbers in terms of their prime factors. I think it's generally a good way to think about them. So we got this number here and it's just a bunch of prime factors, right? Let's say that maybe it's like, it's 2, it's 3, it's another 2, and it's 5. So that's 60, I think. And if we wanted to square that, that should give us like 3,600, right? But what are we actually doing when we're squaring it? Well, we're basically saying there's going to be another 2, another 3, another 5, and another 2. So we're basically just multiplying the number of prime factors of each type. If we wanted to cube it, well, we're putting in another 2, another 2, another 3, and another 5. And it's getting pretty packed in here right now, so I'm probably not going to go any further. So basically that's the idea, okay? What we want to check is we want to see if these, okay, these exponents here, these, you know, like these numbers over here, or actually let me Let me be more clear about that. We want to make sure that these numbers here, so the values in our factors thing, we want to make sure they have a common factor, at least one common factor that's not 1. Okay, we want to make sure they're not relatively prime because that means it's a power. So how are we going to do that? Well, greatest common denominator. We looked at a GCD algorithm the other day. I'm going to go right for it. So basically const GCD is going to be something that takes two numbers A and B. It's going to check if B is divisible by A. If it is, it's going to actually it's going to do that division. It's going to get the remainder, and it's going to recalculate the GCD of those two things. This is basically our Euclidean algorithm for calculating GCD, greatest common denominator. And let's just return the GCD of, let's say, 12 and 8. Okay, it's 4. Great. That's good. That's what we want. But here's the thing. This only takes 2 arguments, and we might have a situation where we have like lots of different factors that we want to check, right? It might be more than just 2 of them. So because of that, and actually, can we think of an example of that? Let's see, 2 times 3 times 5, that's 30 squared, 900. So let's try that. So if we run this, now we should find, no, it's giving us this. Okay, let's run that. And yeah, so now there are 3 of them. We need to be able to check the GCD of these 3 things, you know, not just a pair of them. So how are we going to do that? Well, like I said, I like to think of numbers in terms of their like prime factors here. So let's take a look at a few of them. Let's go with, okay, what would be some good examples? We're going to do a Venn diagram. This is going to be fun. So let's just quickly take 2 numbers. I think we had 60 already, right? So we had 60, and we found that it was going to be like, what was it, 12, 5. 5 is prime, so this will be 3 and 4. 3 is prime, and this is just going to be 2 and 2. Okay, and then let's get another one. What would be another good example? Maybe like 54? Let's try that, 54. It's gonna be a little tough if you're just serving them up off the top of your head. So this might not work out. We might need to change a number or 2 here, but we'll find out. Okay, so 54, what is that? It's divisible by 6, right? So that would be 6 times what, 9? Yeah, 6 times 9. Okay, so 6, that's 2 and 3. 9 is 3 and 3. Good, we've got some diversity here. This is good. So diversity and overlap. That's what we want. So we've got 3, 2, 2, 5. 2 2s, a 3, and a 5. This is 1 2 and 3 3s. So they have some stuff in common. They have some stuff not in common. I guess I'll just do a quick zoom out so I can fit everything on screen here. And here we'll say in this corner we've got 60, and on this side we've got 54. And we want to take a look at, you know, what's in their intersection here. So they both have at least 1 2. So there's going to be a 2 in here. They both have at least a 3. The thing is, 60 has another 2. It doesn't have any more 3s, but it's got a 5. 54 has no more 2s, but it has 2 other 3s. So this is a way that we can sort of think about the numbers 60 and 54. What's really cool about this is it allows us to do some pretty slick math stuff really quickly. So like, for example, the GCD, the greatest common denominator between these two, is going to be equal to just what's in the intersection. It's just 2 times 3, so it's going to be 6. Whereas if we want the LCM, so the lowest common multiple, like if we wanted to know, you know, if we were multiplying 60s and we were multiplying 54s, what's the first number that they'd have in common? Well, basically, it's just all these things multiplied together. So it's going to be 2 times 3, which is 6, times 3 times 3, which is 9. So that'll be 54, times 10, 540. So 540 is divisible by 60, and it's also divisible by 54, and it's the smallest number with that property. Okay, so that's basically, this is how we're doing GCD. The thing is, now we want to look at something a little more complex, because we want to look at GCD of 3 numbers, let's say. So I don't know if we're just going to modify this existing one that we have, or if we're going to make a new one, but let's say we've got a new number, it's going to be 90. I'll zoom back in for this one. Okay. So 90 is 3 times 30. 30, it's 10 times 3. And 10 is 2 times 5. Okay, so like the other ones, we have some stuff in common, but we also have some differences. And actually, this one's going to be a little more nuanced. Here, let's we'll do a new one with all 3 of these guys. Okay. While I'm sketching this out, and hopefully I don't mess it up too bad, these can be a bit difficult to draw. Has anyone here ever seen a Venn diagram for more than 3 items? Like, let's say 4 items, 5 items. Because that's where it gets really interesting. Let's put 90 up here, and the 2 others will be the same. So we'll have 60 over here, and then 54 over here. And this is going to give us our big GCD. Oh, this is an exciting moment. Okay, so what do they all have? They all have at least one 3, and I'm going to sort of tick them off here. So they all have a 3. Do they all have another 3? Nope, not all of them. Do they all have a 2? Yeah, they do all have at least a 2. So we'll put a 2 there. Don't mix that up with 32. That's a 3 and a 2. Okay, so then what else do they have? This one's got a 2. That one's got a 5. This one just has 2 other 3s. This one's got a 5 and a 3. Well, check it out. So 60 and 90 both have 5s. So we'll tick off the 5. We won't put it in here, but we will put it right here because both of these two have it. What else can we put in here? Well, it looks like 60 is the only one with this other 2. None of these other guys have any 2s. So we'll just put this 2 out here. It looks like 54 has 2 other 3s, but guess what? 90 also has a 3. So we'll put that over here. We can tick off both of these 3s. What's left over? Just this 3. 54 has another 3. So notice, some of these are empty, some of them are not empty. But the main thing that we want to do here is we want to come up with some way of just isolating this middle part right here. We want like just the GCD. We want to jump right to it. That's going to be our goal. How are we going to do that if we have these multiples? We need some process we can follow to sort of break this down. Now, my claim is the following. So check this out. Let's take stock of our GCDs here. So the GCD between, let's say 90 and 54. Actually, let me zoom in that. Oops. Let's just undo all that pen stuff. The font's too big. It's too big. Anyway, we'll move over here. We'll say, okay, GCD of 90 and 54 is going to be what? Well, it's going to be 3 times 2 times 3. So what's that, 18? I'm no good at math. I don't know. GCD of these two... or should we do the GCD of all 3 of them? Yeah, let's do all 3 of them for now. So we'll say 90, 54, and 60. Just putting them in there in no particular order. It's just going to be this middle part here, the part that intersects all 3 of these. So it's 3 times 2, which is going to be 6. Okay, great. Now here's where things get a little more interesting. We know, because we're looking for stuff that's in this zone, right? That's what we're looking for. The only way it could be in this zone is, this is one way to think about it anyway. If it's in this zone, it must be in this zone already, right? It must be in this zone as well as this zone. In fact, it is the intersection of those 2 zones. Let's think about what those zones are, because it's just going to be the GCD of that, whatever it is, right? So we'll say that here, GCD of 90, 54, and 60. My claim here is that it's equal to the GCD of these. So GCD of 90, 54, 60, we're talking about this interior zone here. And I'm saying it's the intersection of this zone and this zone. So let's figure out what those are. Well, this zone over here is just 60. Okay, not too bad. And then this zone over here, well, it'd be 18, right? So 3 times 3 times 2, we found it was 18. But hey, not a coincidence that that 18 is the GCD of 90 and 54. So this is kind of interesting because it means we can basically just keep folding this over and basically just reapplying the function pairwise. So we'll take, if you think about it, this is actually a lot like the way we do multiplication, right? Like if we want to do 3 times 2 times 3, well, we do 3 times 2, and then we multiply the result by 3. Well, doing the same thing here. So if we want the GCD of 90, 54, and 60, we'll do the GCD of 90 and 54, and then we'll do the GCD of whatever that is, and 60. So that's going to be the idea here, okay? Any questions? Let me know if there's any questions. As for now, we have a way of finding our prime factors. We have a way of getting the GCD for, pairwise. But now let's say function big GCD, okay? So if we want like multiple arguments, and we actually want this to work no matter how many arguments there are. So the way we're gonna do this is we're actually just gonna say dot, 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 and what should we call these things? Nums, yeah, nums, I guess, that makes sense. We're using num down here, so okay, nums. Now by doing the spread operator over here, the way it's gonna work is basically the following. So I'm going to do this, console.log nums. Actually, wait, I'll just do a return for now, okay? Return nums, just to see what it's actually getting in here. Oh boy. Typing is not one of my strengths. All right, so big GCD of what? Well, let's try 90, 54, and 60. Okay, so we're giving it 3 arguments. Right now it's just returning nums, so it should be giving back the same arguments, but notice it's putting them into an array. So I didn't have to like put these in an array. I didn't have to use the spread operator here. I'm using the spread operator here, okay? So what I'm saying is what you're receiving has already been spread out. Nums is itself an array. So it's almost like a reverse spread operator. I found this kind of tough to deal with at first, but makes sense. Okay, so we've got our nums here. What are we gonna do with this? Well, basically, what we were saying before. So we'll say let, what should we call it? Divisor? Yeah, let divisor, we don't technically need to give it a value right now, but I will. We'll make it the minimum value of all these nums because, that's the biggest it could possibly be. You can't have a GCD that's bigger than one of the numbers involved. That wouldn't make any sense, right? You can't divide it into that number. It could be equal, but it couldn't be bigger. So we'll start it out as this. And we'll just say while nums.length. Yeah, while nums.length. And we're basically just going to say that our divisor is going to be assigned the value of the GCD of itself and nums.pop, let's say. So we'll just take one of our nums and we'll just GCD it with whatever the divisor is already. Technically it's already one of the nums, but anything GCD'd with itself is just going to be the number itself, so we don't need to worry about that, and we'll just say return divisor. I suppose we could also start divisor as like 1, and I don't think it would make much of a difference or at all, but let's find out. So big GCD, we should get 6 from this, right? We're getting 6. Okay, so let's see. If we take a look at this, let's say we wanted a bigger number, like 18. So we just need to multiply this one by 3. So instead of 60, let's go with 180. And now we should be able to get 18, I think, as our big GCD between all these 3. Let's hope so. I'll be very embarrassed one way or another. Yeah, there we go. What I was going to say is if I got it wrong, that means either I did the code wrong or I did the math wrong. So no real winner there. Okay, so good stuff. We're getting this. It's 18. We're good. It looks like big GCD is working. I mean, if we wanted to, we could just sort of verify this. Let's go with 15 also, and now we should get, I think, 3. Yeah, 3. Okay, good. So looks like this is working for arbitrarily many variables, inputs, arguments. What we want here is, well, let's see what we're actually getting. So we're getting this stuff back, right? And what we're trying to check is the GCD of all these things. What are these things? They're the values. So we can just say object.values, whoops, object.values of all this stuff over here, right? And yeah, there we go, 2, 2, 2. So what we need to check here is big GCD of all this stuff is greater than 1. Yeah, because if it's 1, then that means they're, well, it's not a power, basically, for the reason that we saw before. It's not just, yeah, it would mean that it couldn't possibly be the same number multiplied by itself some number of times. That's basically the reason. Okay, so false. We're saying that 900 is not a power. Okay, well, that's kind of surprising. What are we getting for the big GCD of all this? Oh, we're getting null. Okay, probably because this is an array, so we should probably spread that out. And let's run that. Okay, now we're getting 2. We want to check if this thing is going to be greater than 1. Let's run that. And I mean, it's only passing 6 out of 10 tests because we're not actually putting the number in. We're putting in 900. What's the number called? It's called n. Okay, so let's put in n there. Let's run that. And there we go. We did it. We did it. Okay, great. That feels amazing. What an interesting problem. So I want to make a few changes here. And while we do that, we'll just sort of recap what we've done so far. So just trip down memory lane here. We started out talking about prime factor trees because we wanted to see what kind of properties do we have in terms of the factors, the prime factor specifically, of powers. Each of these 3 things, these are all powers. I guess I could have given a counterexample of something that's not a power, but we sort of saw those, like for example, I don't know, 6, that's 2 times 3. It's not a power. It doesn't have like, well, what doesn't it have? Let's find out. It's basically, in this case, this is all the same prime factor. They're all the same. In this case, we have different prime factors, but we have the same number of them. In this case, we have different prime factors and we don't have the same number of them, but the numbers of them that we have common multiples, which means that we must have started with some number, in this case 12, and multiplied it by itself. We could have also multiplied it by itself more than once. So like, for example, this is what 60 cubed would look like. And that would be a pretty big number. I don't know, 256,000, something like that. Anyway, moving on, what we found is that if we want to get the GCD of 2 numbers, it's, or wait a sec. Okay, why are we talking about GCD? Well, basically, GCD stands for greatest common denominator. We wanted to make sure, because if these are, like, if they do have common factors, then, oh, and I might have said common multiples a minute ago. Every pair of numbers has common multiples, but what I mean is common factors. So these have to have common factors. So how do we check that? Well, we find the greatest common denominator and see if it's greater than 1. If it's 1, then they're relatively prime. They don't have any common factors. But if it's greater than 1, they must have some common factors. So basically we just multiply the number. Okay, or some number anyway. So we need a way of checking GCD. We're using our Euclidean algorithm. We learned about the Euclidean algorithm a while back. We ended up using it in a previous task called count black cells. I don't remember exactly what number that one was, but it's called count black cells, and it was the last one before that that array section that we just finished up, the list. It was the last one of the loop tunnel, I think is what it was. Anyway, okay, so we use our Euclidean algorithm, which is basically this over here. If you want a description, check out the video for count black cells. Going back to this over here, though, basically what we found for GCD is that it's essentially just the intersection of all the prime factors in this Venn diagram. And furthermore, that if we wanted to get arbitrarily many of these, like let's say 3 or 4 or more, then we can just do them one step at a time. So we can say, well, you want to take the GCD of A, B, and C? Well, it's the same as the GCD of A and the GCD of B and C. Okay, so that's pretty much it. So we did this all one step at a time. We have our GCD function over here. This is just for pairs. This is for arbitrarily many of these things. We also have this thing for calculating the prime factors. But you know what? As it turned out, we're actually only using the values from this thing. So I'm thinking, why bother? Why bother? Why bother with finding the object.values of this thing? If we only want the values, let's just return the values. Okay, so let's just make this an array, back to an array. We started with an array. We're going to move it back to an array. And instead of this, instead of factors at D is going to be instances, we'll just say factors.push instances. Is that going to work? Because basically it's only going to put them in there if there's at least one of them. Okay, so then, yeah, I think that should work. I could be wrong, but let's try running that. We'll see if that works. So it's a bit simpler. We don't have to worry about that like object.values kind of stuff that we were looking at a second ago. So I like that a bit better. In fact, here, let's clean this up a little more because that's just one line. It can go like that. That's a bit better. Yeah, I like that. Good. Nice. Excellent. So what else? This could be a const. Doesn't need to be a let because we're not going to reassign factors. And you might be thinking, well, yeah, you're pushing numbers to it, but keep in mind, it's not a constant array. It's not that we're not changing the values in the array. It's that it's a constant binding between the word factors and whatever array we have here. It might have different stuff in it over time, but the binding is going to be constant. We're not going to be able to say factors later on is like some other thing, okay? So we're doing big GCD of this thing over here, but I just noticed something, you know, we're spreading this out, but we're also spreading it out to call it. We don't need to do that. We can just give it an array of numbers, okay? So we can do something like this, and that simplifies things quite a bit, I would say. So this is great. This is a nice little algorithm we have here. Folks, I love this. I think this is one of the nicest algorithms we've written. This is super mathy. It's very functional, lots of functions working together here, you know, like we basically just declared 3 functions and then just called it and compared it to 1. That's pretty much it. That's all we're doing here. So this is a nice algorithm. I really like this. Like, I'm pumped about this one. I think this is some of the nicest stuff we've written so far. Okay, so on that note, I think that's probably about it for this one. Yeah, I think we can probably finish up with that.